Hi, I am KHAIRINA and I'm going to give some introduction about our topic, which as we know, infrared IR spectrum is widely used analytical technique in chemistry that is used to identify and characterize the chemical structure of organic compounds. We were given this assignment to identify the functional groups and the chemical bond presented in the butyramide, which is an amide with the molecular formula C4H9NO by analyzing its IR spectrum that measuring the absorption of IR radiation by molecular vibration in the compound. In the IR spectrum of butyramide, characteristic peaks can be observed at specific frequencies or wavelengths, which correspond to specific vibrational spectra of the molecule. This peak can be used to identify the functional groups in the butyramide, such as amide group CO and H2. According to a study published in the Journal of Molecular Structure, there were absorption peaks observed in the spectrum due to the characteristic vibration of the functional groups present in the butyramide, including N single bond H stretching vibration, C double bond O stretching vibration, C single bond H stretching vibration, and C single bond N stretching vibration. These findings confirm the presence of the amide functional groups in butyramide.
For the body peak assignment, the NH stretching peak in the infrared spectrum indicates the presence of an amide group, which in turn confirms the presence of butanamide. In the amide functional group of butanamide, the nitrogen atom is bonded to a hydrogen atom. When infrared radiation is passed through the sample, it interacts with the molecules and causes specific vibration of the chemical bonds. The NH stretching vibration occurs when the NH bond elongates and contracts. This stretching motion generates a characteristic peak in the IR spectrum. In this figure, as you can see, the peak is observed as a broad band in the range of 3200 to 3600 cm-1. The broadness of the peak is often due to the presence of hydrogen bonding between the amide groups in the sample. By identifying this NH stretching peak in the butanamide IR spectrum, we can conclude that an amide group is present in the molecule. Since butanamide is an amide compound itself, the presence of the NH stretching peak confirms the presence of butanamide in the sample. The C double bond O stretching peak in the infrared spectrum is characteristic of the amide bond and provides additional support for the presence of the amide group in butanamide. In the amide functional group of butanamide, the carbon atom is double bonded to an oxygen atom, forming a carbonyl group. The C double bond O bond exhibits a specific stretching vibration that can be detected in the IR spectrum. When infrared radiation interacts with the sample, it causes the C double bond O bond to stretch and contract, resulting in a distinct peak in the IR spectrum. The C double bond O stretching peak for amides is observed in this figure in the range of 1650 to 1700 cm-1. By identifying the C double bond O stretching peak in the butanamide IR spectrum, we can conclude that an amide bond is present in the molecule. Since butanamide is an amide compound itself, the presence of the C double bond O stretching peak provides further evidence for the presence of the amide group.
Okay, now we continue with the body peak assignment, which is CH stretching. CH stretching vibration in a butanamide can typically be divided into two regions, which is the first one, a strong broad peak in the region of 2800 until 2900, corresponding to the stretching vibration of the methylene group, which is CH2. And the other one is a sharp peak in the region of 2900 until 3000, corresponding to the stretching vibration of the methyl group, which is CH3. The position and the shape of the CH stretching peak in the butanamide can be used to confirm the identity of the molecule and distinguish it from the other compound with similar functional group. For example, the position of the CH2 stretching peak can be used to distinguish butanamide from other amide or ester with different alkyl chain length. It was nothing that the CH stretching vibration in an IR spectrum can sometimes overlap with the other peak, making it difficult to assign them definitively. However, in the case of butanamide, the CH stretching vibrations are typically well reserved and distinguishable from the other peak in the spectrum.
The amide functional group combines the features of amines and ketones because it has both NH bond and the C double bond O bond. Therefore, amides show a very strong, somewhat broad band at the left end of the spectrum in the range between 3100 and 3500 cm-1 for the NH stretch. At the same time, they also show the stick-shaped band in the middle of the spectrum around 1710 cm-1 for the C double bond O stretch. As with amines, primary amides show two spikes, whereas secondary amides only show one spike.
The explanation of the key features that might be observed in the IR spectrum of butanamide. First is amide C-double-bond-O stretching. The most prominent peak in the IR spectrum of butanamide appears in the range of 1650 to 1750 cm-1. This is because the C-double-bond-O bond is a relatively strong one that can absorb energy at this frequency, causing it to vibrate. This peak corresponds to the stretching vibration of the carbonyl group C-double-bond-O in the amide functional group. In the case of butanamide, it would typically expect to see a strong and sharp peak in this region. Second is enhanced stretching. Butanamide contains an amide functional group, which includes an NH bond. The enhanced stretching vibration usually appears as a broad peak in the region of 3100 to 3500 cm-1. This is because the NH bond is a relatively weak one that can absorb energy at this frequency, causing it to vibrate. However, in some cases, this peak may overlap with other functional groups and appear less pronounced.
Hi, now I will continue with interaction between them. First, for C-double-bond-O stretching, the C-double-bond-O stretching vibration in butanamide is influenced by the electronic and steric effect of the carbonyl group. The C-double-bond-O exhibit partial double bond character, and the stretch's frequency is affected by factors such as electronic environment, conjugation, and neighboring functional group. The presence of electronegative atom or groups adjacent to the carbonyl carbon can influence the bond strength and affect the C-double-bond-O stretching frequency. Then we move to enhanced stretching. The enhanced stretching peak in butanamide is broad and often indicates the presence of hydrogen bonding interaction. The amide hydrogen can form hydrogen bond with another electronegative atom, such as oxygen or nitrogen. Hydrogen bonding leads to the redistribution of electron density and affect the strength and length of NH bond. Okay, as my friends ALLYSYA explained about the peak of CH stretching, then I would like to add some information in interaction of CH stretches. CH stretching vibration occur in the range of 2800 to 3100 cm-1 in IR spectrum. The CH stretching vibration in butanamide is arise from allopathic carbon-hydrogen bond in the molecule. These vibrations are influenced by the bonding environment and neighboring functional group. The intensity and frequency of CH stretches peak can be affected by factors such as hybridization of the carbon atom, the presence of adjacent functional group, or substituent, and the electronic effect on the nearby atom. The strength and frequency of CH bond can be altered by this interaction, leading to the variation in the observed stretching vibration.
Okay, I would like to simplify the summary of IR stretching frequency in butanamide. So the first one is carbonyl, C-double-bond-O. The range start from 1650 till 1750 cm-1. Then amide and H bond. The range start from 3100 till 3500 cm-1. For alkyl, CH bond. The range start from 2800 till 3000. While for the last one is CN bond, the range start from 1250 till 1350 cm-1. They can be read on fingerprint region, but usually we don't analyze the fingerprint region, which contain complex pattern absorption peak. So note that IR spectrum provide valuable information about the vibration of functional group, but it does not provide a complete picture of the interaction within the molecule.
So overall, we can conclude that the compound is butanamide because of these three reasons. The first reason is NH bond. This bond proves that there is presence of amide functional group in the compound. This bond is the weakest bond compared to the other two bonds that we can observe in between 3200 to 3600 cm-1 in the spectrum. Secondly, the C-double-bond-O, which is the carbonyl group, this is the strongest bond as the stretch is the strongest one compared to the NH bond and CH bond. So we can see it between 1650 to 1750 in the spectrum. Okay, lastly is the presence of alkyl group, which is CH bond, which is present in the spectrum. This is a weak bond where we can observe it between 2800 to 3000 cm-1 in the spectrum. The length of the alkyl group also helps us to determine what type of amide, whether it is propanamide, butanamide, pentanamide, and so on. Okay, why we determine it is as butanamide instead of butanamine? Obviously because it has amide group which consists of carbon, hydrogen, oxygen and nitrogen. Meanwhile, amine group only consists of carbon, hydrogen and nitrogen. When the atoms is different, it leads to different boiling points. As we can see, the upper one is butanamide and the lower one is butanamine. Look at the dotted lines. It shows that butanamide can form hydrogen bond between butanamide's molecules. Meanwhile, butanamine cannot form any hydrogen bonding between the molecules. When the molecules can form hydrogen bond, it automatically has higher boiling point because hydrogen bond needs more energy to break the bond. So, that's all from us. Thank you.